Ash, take it away.
Hello, hello. Some of you guys know us from yesterday. We hosted a lot of you, 50 years. So right now I'm at 50 years as the bio lead for it. But before I joined 4 months ago, I was actually doing my PhD in Canada on T-cell development and thymic regeneration. So my study was trying to understand the immunosenescence and how to develop technologies to reprogram that. We ended up spinning a company out of the work called Notch Therapeutics, where we program immune cells for cancer. But that was a pivot. We actually wanted to do lymphopenia and immunosenescence. So today, the challenge I'm going to talk today is about reversing immunosenescence to regenerate the aged immune system. So 2 questions. What are T cells? Which is kind of an obvious question, especially today with COVID. But T cells are probably arguably the most important cellular component of your immune system. They regulate different immune cells in your body, but they also have immunosurveillance, so they can recognize when a cancer is emerging and kill it. So they're a very important part of your immune system. And in the context of aging, you lose their functionality or you lose the quantity of those T cells and what they can see in the body. I have a question for all of you. Does anyone raise hands up if you know what a thymus is? Oh, that's good. That's fantastic. A lot of you do. So while other blood cells in your body develop in the bone marrow, T cells actually develop in the thymus. So if you find a way to regenerate the thymus or make sure that it's a conducive environment for T cells to develop, then you have a way, to reprogram or regenerate the immune system. So there's several hallmarks of T cell aging. One of the main ones being Thymic Involution. So this is the organ that I told you before, develops T cells, but it also becomes very fatty and becomes very, very small in its structure. So at 40 years old, you only have shreds of this organ left for you, and you no longer have a conducive environment to make immune cells to treat cancer or to even make sure you're not sick from infections. But there's also other hallmarks of T cell aging as well. One of them being immunodeficiency. So if you have an aged T cell component in your system, then you are immunodeficient, therefore you're not able to mount a proper immune response. You also have a repertoire reduction, which means that when you have all the T cells in your body, you have a diverse amount of T cells, you recognize every possible antigen or bug that comes into your system. But with an aged immune system, you have a shortening of that repertoire, so you're able to see a lot less things. So now when you're 80 years old and you have a bug that you've never seen before, you're no longer able to mount the proper immune response to it. Another thing is inflammaging. So some have argued that the reason why we have all these incidences of cancer when we get older is because of inflammaging. So these senescent immune cells kind of persist in your body. They produce these inflammatory mediators that give rise to cancers and different diseases as well. So in effect, if you're able to regenerate the whole T cell compartment, make it young again, you can avoid all these hallmarks of age. So this is I wish maybe we'll dim the lights or not, but this is an immunofluorescence picture of the thymus that you took in grad school. You take a mouse, a young mouse, you take its thymus out, cut it, take a section of it, and then use immunofluorescence, so tag different components of it with antibodies to understand the microenvironment of it, to show what a young thymus looks like versus what an old one looks like. The young one looks like, over here, you can see the cortex, which is the outer structure of the thymus, and you have the middle structure called the medulla. This right now is a conducive environment to make immune cells, to mount an immune response, and have a functional immune system. But in an older mouse, which you see here, and you can compare this to an older patient or an elderly person, there's no structure at all. There's a mix of the medulla and the cortex. So if you found a way to make this old thymus into this young thymus, then you have a way, in effect, to regenerate your immune system. And that's the strategy people are trying to work on today. So just quickly, what T cell development is, because this is the T cell this is the type of immune cell we're trying to regenerate, is you have a stem cell within your bone marrow. It can become any blood cell in the body. If it goes into the thymus, it recognizes a microenvironment that allows it to become a bona fide immune cell or T cell to recognize antigens and mount an immune response. But it's really, the interesting thing about this is it's really the crosstalk between developing immune cells in the thymus and the actual microenvironment that gives rise to a fully functional thymus. So a lot of the strategies try to mimic T cell development within the thymus so you can have a fully functional thymus system. So I want to touch on the main way people are trying to regenerate the immune system right now. And it's simply a bone marrow transplant. So we kind of use that from methods we use for immunodeficient patients, or if you have AIDS, or if you have cancer treatment, like radiation, all that. The best way to regenerate these patients' immune system is to just give them a stem cell transplant. You take out stem cells in the bone marrow, give it to these patients, and hopefully you can have a regenerated T cell compartment. The problem is that because the thymus degenerates so quickly, and because it's no longer, as I mentioned before, a conducive environment for these T cells to grow in, you have a very slow recovery of the T cell compartment. So after 3 years, or even 5 years of an elderly person, no matter how many stem cells you give to these patients, you're no longer able to regenerate the whole T cell compartment. So we need much better strategies, and this is the challenge I propose to everyone to think about today. So there's several different strategies people are working on, and you can break it down to 4 kind of circles, or 4 compartments. The one is you can target the microenvironment of the thymus. So as an organ, you can target the thymus microenvironment to make it more conducive for T cells to develop in. The second one is you can modulate hormones, because what we do know about thymus biology is that during puberty, androgens, different hormone levels, can reduce the efficacy of the thymus to actually produce T cells. Another one is cellular therapy. This is what I'm biased toward, because this is what I worked on. And the last one is targeting actual hematopoietic progenitor cells, it's targeting stem cells to be able to go to the thymus and regenerate it. But despite all the knowledge we've gained about thymus biology and all the different strategies people are trying, there's still a lot of challenges left. One being, if you're trying to develop biologic or gene therapy, there's no specificity to the thymus. Kind of a niche organ that sits above your heart, and there's really no way to target specifically the thymus microenvironment. That's a big problem still. There's physical barriers to a cell-based approach. And I'll talk about the approach that we tried in our lab, though, but when you're trying to develop a cell-based approach to it, it has to get into the organ and actually do its thing. But because of the physical barriers of this organ, you can't actually get inside there. The last one is there's still a lack of understanding, which is very much a difficult thing to kind of solve. It's a lack of understanding of the thymus microenvironment. We know these immune cells develop in this thymus, but we don't exactly know the different components, the different cell types within this thymus that allow for this T cell to develop normally. And a big thing is the lack of preclinical models, which is a big problem in the field. A lot of the times we try to do aging research in older mice, which could be fine for other organs, but it's terrible for the immune system. So we use, some of you may be familiar with humanized mouse models, where you genetically alter this mouse so it can now take different human immune cells and not reject it, which is a great model to study other stuff, but it's a terrible model to study the immune system. So we need new preclinical models to actually test all these strategies for thymic regeneration. So the strategy we use is iPSCs. Some of you are familiar with it. You take a terminally differentiated cell type, you reprogram them into pluripotency, and based on our understanding of how different germ layers develop, you can guide them towards T cells, or in our case, progenitor T cells. And the idea is that if you take these progenitor T cells and give it to a patient, an older patient, what we've seen is that it can go through the whole blood system, go to the thymus, and through this crosstalk mechanism mentioned in the beginning, you're able to regenerate the thymus a little bit. But it's not working as well. It's very expensive to do a cell-based therapy, so we need better and cheaper alternatives for sure towards it. And the main goal that the field is trying to work on is basically, you take a young mouse, you have this beautiful thymus, you take an older mouse, you have it degenerated, find any strategy to reprogram it back into the young cell state. That's kind of the big challenge, it's kind of the big goal of myself and other people within this field. So the question that I have for everybody, are there cheaper and more effective alternative approaches? If you look at the little tree that is in the slides, I mentioned some of them. You can have a sex-stored ablation, you can have a cell-based version of it, you have biologics, but because of the challenges I mentioned before, we don't have a consensus of what exactly the strategy may be. So I was hoping a lot of you, with this information now, can kind of help ideate and develop some new strategies to kind of reprogram the thymus to make it more conducive for T cell development. That's all I have for you. Thank you.
So how about autoparabiosis for regeneration? Keep your blood while you're young, inject it when you're older, and hope that that will help your thymus.
Parabiosis, actually taking someone else's young blood and putting it inside you?
You're wrong. Even better.
Autologous.
Autologous approach. I take my cells, maybe store it, and then give it to me when I'm older. That is one approach, but I think that is one approach. The idea behind that is you're going to keep all your diversity of immune cells, you freeze it down, and you thaw it again, and give it back to the patient. That is a possible approach for sure. Yeah, I don't think people are working on that, but that is an option.
So there's the direct injection. You directly inject the thymus without killing 0.2% of your elderly population, which tends to happen for deep internal injections, then pretty much everything in the list works. You can put in any of the sex sterilization medication, you can use KGF, you can use growth hormone. I mean, it all works great. The growth hormone got trialed in humans, failed because you can't give humans the same amount of growth hormone that you give mice. There's also the calycine peptides, which I'm currently testing on myself, which have data in Russia from the last 30 years showing reduction in mortality in late life, and also, if you want to look at data, regrowth of the thymus in mice. Nobody's actually shown that it regrows the thymus in humans. For all we know, it's causing growth or replication. But there's any number of approaches you can just get over this issue of how do you get the thing into the thymus. And I agree that your cell approach is one of the better ones, because at least then you have cells that know they're going to the thymus, and probably innocuous Unicof's lab, I believe, has shown that you can use various cell types for this. It's all just, how do you corral these things and get people to give you money and get the clinical trials done, in my mind. That wasn't a question.
No, I agree, actually. Well, to your point, the KGF, the biologic approach is great, but the biggest issue is just not specific enough. If you can guide that biology towards the thymus, then you have that therapy for sure.
Given that athymic individuals who've had their thymus removed in their first year of life seem to develop normally and have fairly solid immune systems, couldn't this whole immune system rejuvenation be done ex vivo? And how do you view this in light of athymic individuals?
Right. So the athymic individuals they're referring to obviously have no thymus, but because you develop all the repertoire of T cells you need when you're basically born, you don't need necessarily the thymus later on in life, right? You've already developed it. It's only in that individual when they get older, which we don't know yet because it hasn't been that long. But when they get older, they're going to start to see problems more than likely.
But doesn't this suggest then that you could do all this work ex vivo? You don't necessarily have to have an in vivo thymus.
Oh, agreed. I agree 100%. If you can develop, some people are working on that now, if you can develop the thymus outside the body, but take that person's immune cell, progenitor cells, put that in the ex vivo compartment, and then develop the repertoire, and then put it back in that same patient, that could work for sure. Sounds easier, but absolutely, that could work.
I've heard that for some cases where people have their T cell repertoire ablated, that afterward, various horrific things that they're going through, the least of the lesser of evils kind of thing, that weirdly there's some sort of homeostatic mechanism and their thymus can spontaneously regenerate even later in life. Is that really true?
Yeah.
What's going on? How does it work?
Yeah, it's more for younger people, that rebound of the thymus. When you're older, because you only have shreds of tissue left, it's a lot harder to do that. But the homeostatic expansion for T cells is a real thing for sure. The idea with the body's smart, so you always have the same quantity of T cells going around your body, which is fine for that. The problem is the diversity of that T cells is restricted. So although you have 1 billion T cells inside of it, but what they recognize is not.
If, say your thymus involutes, in your late teens or something, it's even later than that, right? That the thymus can sort of bounce back after a T cell ablation. So could people intensively study people who are going through processes like that to try to understand what that mechanism is?
Right.
Which the
Absolutely. The reason I mentioned the name Dudikoff lab, they do exactly that, how to endogenous repair the thymus, how it normally bounces back. Learn from that and then apply it to older patients, so absolutely.
Did you mention Ligenesis?
I did not. Sorry?
Ligenesis, they're also doing, after the liver ectopic, they get tissue from the fetal thymus implanted in the lymph node.
Oh, cool.
And you get an ectopic, so you get a thymus that's outside the normal area, but it's just a cell factory.
Exactly. Blood can go anywhere, so that works as well.
They tend to lodge in lymph nodes.
Pardon me?
They tend to lodge in lymph nodes.
Which what does?
Well, for instance, I know that the hepatocytes or hepatoblasts or whatever they are, their progenitors that they inject to rescue mice that have had their livers removed.
Yes.
The hepatocytes lodge in lymph nodes and grow like tiny little livers disseminated
Is that
around
cool?
that provide enough liver services to keep them alive.
Yeah, same with the thymus. It doesn't really matter where you put it. If you take a little tissue, put it somewhere else, there's still blood flowing through it. So just, it'll go through the thymus and provide you a brand new repertoire for sure.
They have a complex, multi-layered structure.
Let's get a little piece, put it somewhere.
Like a lymph node with cortical.
Well, no, sorry. Ideally, you still have the architecture there. You don't need the whole thymus, but you still need that medulla, the cortex. That architecture still needs to be there because that's required for T cells to go through all their stages. Yeah.
So one of the interesting topics, leading on from making mole rats have multiple villi that don't infiltrate, and the human data on calorie restriction, the calorie study, which was only 14% calorie restriction, and nonetheless resulted in about as much thymic regrowth as Greg Mahoney's group has shown. So that sort of suggests that the people who say, well, it's all connected to inflammation, your evolution is inflammation connected, and maybe you can get as much out of that as you would get out of many other therapies. If you can just dial back the inflammation, maybe you get a meaningful amount of thymic growth out of that. Who knows?
No comment to that, but it's an interesting point. Thank you. Thank you.